Good evening. Thank you for joining us this evening. My name is Ron Crodogino. I'm the president of the Montreal section of the Canadian Academy of Engineering. I want to welcome you to the webinar this evening on the subject of the history of space research and technology innovation in Montreal, Quebec, and Canada. Okay. The Canadian Academy of Engineering is a self-governing nonprofit organization established in 1987 to serve the nation in the matter of engineering concerns. Its mission is to recognize and honor outstanding engineering achievements and service to the profession, and to demonstrate leadership and responsible applications of engineering knowledge for the benefit of the Canadian public, and to provide strategic advice to decision makers and to contribute to shaping the future of engineering. The Montreal section has complementary missions to create more frequent opportunities for fellows to participate in the local fellows to participate in the activities of the CAE, to create opportunities for interactions among the fellows, and to discuss issues of local interest and their intersection with the national issues. We aim to serve these objectives in our seminar tonight. Our speaker has expressed the desire to speak to an audience rather than a computer screen. So we had to find a venue, and I want to thank McGill University for making this venue available to us in the Faculty of Engineering. Particularly, I want to thank Dean Jim Nysel and his staff, and here again, particularly Katja Martin. We hope that these arrangements will serve to create a welcoming atmosphere for all of you online. Today's seminar addresses one of Canada's best kept secrets: the strength of the Canadian space program, its origin, its record of achievements, the impact this technology has on Canadians' needs and priorities, the impact on Canadian society and society globally, the commercial successes, and the potential for this, for continued Canadian leadership of this technology. We're fortunate this evening to have two fellows who have played a major role in developing the Canadian space technology: our moderator, Richard Boudreau, and our speaker, Mark Donato. I wish to introduce the moderator, Richard Boudreau. Richard is a fellow of the CAE, of CAE and the Royal Society of Canada. He has been involved with space technology and markets for in excess of 40 years. He's a repeat entrepreneur with 13 successful STEM corporate ventures. He's an adjunct professor at École Polytechnique and the University of Waterloo. Serving as Canadian Space Advisory Board, he was an advisor to two ministers and instrumental in getting funding for the space mission, space station mission, the radar set constellation, and also the modification of the Canadian contribution to the 30-meter telescope project. He wrote the first strategic plan for CSA on Moon and Mars missions. I will thank you for agreeing to moderate this. I will now turn it over to you, Richard.
Thank you. First thing first, get installed. And it is always a great pleasure and challenge to moderate Mark. And so hopefully things will go very well. I'd like first to recognize that we're now on ceded land from the Haudenosaunee tribe, Iroquois in French or in English as well, and recognize that we are on their land. One thing that people do not know about the space sector, it's a very little known fact that Canada is the only country in the world that has a positive trade balance in space. So there's no other country like us. And to a large extent, Mark has been delivering on this promise and on this trade activities. Mark and I have been trying to figure out who's the elder for a while. And since we already have 40 years of experience each, we found out a few minutes ago that he's older than me, so I will be nice. However, I will try to keep it on schedule, which is always an interesting thing. Mark has worked in essentially one big company for most of his career. He worked at MDA, EMS, and SPAR. They were all ceded to different companies and sold, and he's been working there as one of their executives for essentially 40 years. He was the COO of SPAR Montreal. He also operated SPAR Toronto and the Moon and the ExoMars rover project. He has had more than 600 people to work with him, which is quite a large factor. It's hard for us to be only one with him, and I think 600 with him would be a nice balance. He is an active leader in the community, very much in the Montreal aerospace scene. He's essentially on all the boards of the organizations, including the schools, like McGill, Polytechnique, and a few others. Mark has a bachelor's, master's, and PhD degree from McGill. And he has done his postgraduate work, or at least his postdoctorate work at Göttingen in Germany. He loves karate, so it's a good idea to be nice with him, but he loves hot peppers and sauces. And so I will leave you to Mark.
Tell everyone if they want to ask a question, to use the Q&A button.
Please, if you ask a question, please use the Q&A button on your screen so I can read it and relay them to Mark. I am very creative, so if you don't write anything, I will invent something.
Thank you, Richard. And as you told me, your most important job is to cut me off when the time is due. So I'm going to better get going. Good evening, ladies and gentlemen and colleagues. I'm going to tell a story of that starts with the Gramophones and that ends up with our space program in Canada. And this story follows pretty much a straight line, but I don't, there's no way I can touch all the innovations that we have done in the space program or in the communication technology in the time we have. So I will just touch on some of the highlights. Now, Canada is a country for which space is very important. It has vast territories. It has a sparse population. It has the longest coastline of any other country on Earth, and it has close to 6,000 communities, 60% with 1,000 or less people. So it's extremely important. the resources we have from space, if we didn't develop them here, we would have to buy the services from other countries, which and we wouldn't develop the technology over here. Canada is a culture of inclusion. We need the telecommunications to talk to our people. We need telemedicine because of the sparse community and the communities up north, and we have national public broadcasting. But we also have agriculture, and we have forestry and mining that is very, that space projects or space satellites are a great contributor to. We have security with the illegal vessels coming into our long coastlines. And we have to monitor the northern shipping lanes, mainly monitor for ice. So this story begins in the 1800s. In 1899, Emil Berliner established his gramophone company here in Montreal. He was a German inventor, and he was hired by Edison to develop a microphone for his phonograph. So that was in the 1880s. And then he left Edison, and he thought the phonographs had these wax cylinders, and everyone had to be an original. You couldn't copy them. So he thought of this flat records that you could make a press, and you could make a mold, and you could reproduce many of them. So he started the Victor Talking Machine Company in the US. And a few years later, he left the US and started the company here in Montreal in 1899. So he opened his factory on Lunar Street at the corner of Saint Antoine and Saint Henry over here. And there's a picture on the left here of the building. He's the one who actually got this logo, which is, I think, the most famous logo in all of history, the dog Nipper looking at the gramophone with the statement, "His master's voice." That was Berliner's motto, "His master's voice." And the dog looking, it was an English painter called Francis Barrault. I know it's a French name, but it was an English painter. And he had painted this dog logo with phonograph, with Edison's photograph. But Edison didn't want it. So Berliner thought of this, and he asked Barrault to repaint over the phonograph with his gramophone. And basically history was made with this logo. So Berliner kept developing. The first gramophones were like hand operated, and he developed with this guy Roy Eldridge a spring and then a governor system to fix the speed at 78. And they built a big business, and they licensed his product in Europe. There was His Master's Voice in England. There was Berliner Gramophone in Germany. It became Deutschen Grammophon. So Berliner in 1922 is getting older, so he sold this company back to the US company. So then in Montreal, we have the second image. It was the Victor Talking Machine Company of Montreal. And if you look at old records, before 1922 are the Berliner Gramophone Company of Montreal, and after that, the Victor Talking Machine. And they called them Victrolas instead of gramophone. The Victor Talking Machine Company was greatly expanded. They were in Japan, like JVC, the Japanese Victor company. And what was coming up in the 1920s is radio. Radio had just started. In fact, there was an exposition by a museum last year. And it basically, for the 100-year anniversary of radio broadcast, it started in December 1919. And the radio broadcasts were experimental. It was an experimental station. But soon after, there were two radio stations that split 12 hours each, CFCF and I think it was CJMS, who were the two first radio stations. Eventually, CJMS moved off the radio station. So at first, radio was seen as a method of communicating verbally, not broadcasting music or anything like that. But as they were developing their radio and going further and further out, they went to Berliner and asked to borrow his gramophone, and basically started broadcasting music, and they would test it how far it would go. So radio kept developing at exponential speed. And in 1928, the biggest radio company in the world, Radio Corporation of America, bought the Victor talking machine company, the biggest gramophone company, to become RCA Victor. They saw a lot of synergy in the electronics and the amplifier and combining that with the gramophone. So you had RCA Victor. There was the plant in Canada, and there was one in the States. And this continued through the 30s, and the 40s came the war. In the war, RCA Victor developed the radios that the military used. So they had a government division, and they kept developing this. And finally, in 1958, they split it into the commercial and the government division. But what happened then in December, I think it was December 1957, is that Sputnik went up, the first satellite. It only had a transmitter on there, and went beep, beep, and you could kind of tell a lot by the Doppler shift, et cetera, et cetera. But I sent Sputnik 1, Sputnik 2, and pretty soon after, the US sent Explorer 1 and Explorer 2. But this company, AT&T, figured out that it would be useful to have a repeater. If we could put a repeater on the satellite. What's a repeater? A repeater is something that takes a very weak signal, reamplifies it, and retransmit it. So they said, well, it would be great if we could get a repeater. So AT&T started working on that. And the US government, like, literally panicked because they couldn't have a private company having this power of transmitting a signal anywhere in North America. It did take a 30-meter dish to transmit the signal up and a 30-meter dish to receive it, but yet they started 4 months later, they started working on the NASA relay satellite. So they went to RCA in the US, they asked to build this repeater in the sky, the satellite, and they came to Montreal because we were the experts in repeaters. We had got the contract for the telephone line across Canada, which was a whole bunch of repeaters and reamplify and go to the next station, reamplify. So we started working in 1958, right here in St. Henry, on the first communication satellites. It was built over a 4-year period. So it was built at the same time. They were all built at the same time. It might have been launched second or something like that. So right here in Canada, we were in the first nations to send a communication satellite. And after we started working on this relay satellite, 4 months after, Canada started its own satellite program, the Alouette satellites 1 and 2. So the Alouette satellites were built, the body of it was built in CRC, the Communication Research Center. And then the electronics were built where the experts in electronics right here in St. Henry at RCA. And the antennas were long dipole antennas. And this picture, you don't see them. They're where those holes are in the middle, because it had 2 11-meter dipole, or just tubes, if you like, and 2 22-meter dipoles. And the company that had the technology for that was the Specialty Product and Research Division of de Havilland. So they had worked on the Arrow, and they had the STEM technology. So these are the 3 companies: RCA over here, de Havilland, and CRC that built this. And the first ones for the electronics, I remember, being told by Lauren Keyes, who was a chief scientist, how they would work with the universities. They had the universities, they would get them to send their best student. They would keep them for 6 or 8 months. They would have a new one, overlap for 2 months. And it went like that for the creation of these repeaters for these first satellites. Now, I'm going to talk about satellites, so maybe I'd like to mention a few things. just a question of definitions. The orbits, when we say LEO or low Earth orbit, we talk about 400 kilometers to 2,000 kilometers. Maybe a little lower, maybe it goes down to 300, but pretty soon you get atmospheric drag. 400 kilometers is the orbit of the space station. And then you have MEO orbit, medium orbit, where you're farther from the Earth, but so you have a bigger field of view and a better field of view of the satellites. So satellites like the GPS satellites are in MEO orbit. Now you say, why does it go up to 35,780 kilometers? Well, that's because that's the geostationary orbit. And the geostationary orbit is called that way because it's the orbit in which the satellite always stays over your head. Arthur C. Clarke wrote a seminal paper on geostationary orbit, and they said we could put a repeater in a geostationary orbit. So he in fact wrote this paper, and that orbit, if you're like the space station, you go around the Earth in maybe an hour and a half, and as you go further and further away, you take longer and longer. And if you're in an orbital orbit and you're at geo, you basically take 24 hours to go around the Earth, and the Earth takes 24 hours to turn on itself. So, that the satellite basically stays over the same place, over the same country, and can be used for telecommunication. Also, a satellite is composed of a payload and a bus. Payload is what's mission specific. It's your communication package, it's your radar package, your camera package. It's for the mission, and the bus tends to be more generic. So you have the thrusters, the solar arrays, the attitude control subsystem, the thermal control subsystem is part of the bus. And the payload, of course, has the transponder, which is a repeater, and the antenna, or it has other instruments. Okay. So, so the first geosynchronous satellite Canada built was ANIK. ANIK was chosen as the name because ANIK means little brother in Inuit, and it was a reference to connecting everybody with the satellite. Now, you still needed about maybe 5 or 10 meter dish to get the signal, but you did get the signal, and you could get it anywhere in Canada. So that was our first geosynchronous satellite. We were in fact the second country in the world to have a geosynchronous. There's only one who made it up there before us. It was Syncon, and it was built by used aircraft. So somehow I have to. So as we go along, there was ANIK B, but in 1976, in 1975, Larry Clark, he bought that division of de Havilland, the Specialty Product and Research Division, or SPAR, the acronym, and he bought it and formed a company with it. And then right away, he started buying the other company that was working on satellite, namely the RCA Government Division. So, so by 1976, you had SPAR Aerospace Limited, which was formed of those two companies. Now, also, we had been working in the RCA building in St. Henry, but it was getting way too small, and we needed antenna ranges and all that. So they moved in 1972, they moved the building, it was RCA at the time, to the bout de l'île, the end of the island. And it was right in Sainte-Anne-de-Bellevue. And this is a picture of the plant as I think it stood last week. So a drone picture of the plant, which was expanded numerous times, I have to say. So as we keep on going, there was the ANIK C series of satellite. And what was notable, well, they were again the most powerful satellites, and they introduced the KU band. KU band is a higher frequency. C band is 4.6 gigahertz. KU is 12.14. And you get more bandwidth, so you can get more information. So it was really ideal for television channels because you could get more television channels on a satellite. So ANIK C had a 24 transponder chain or chains that could carry 24 TV channels, and they were analog. They were put on a carrier, but they were analog transmission at the time, and that ANIK C introduced direct to home, where you could have 2-meter dishes and receive a TV signal. So you remember those 2-meter dishes on the hotels and brasseries, and few people who were lucky had it in their backyards. Well, that I remember Lauren, in fact, Lauren Keys, who was working on this, saying we looked at that and we were wondering, is it possible? Could we actually send it to a 2-meter dish at home? Could we have enough power, enough gain from the antenna? And they in fact succeeded in doing that. So we were the first country to introduce direct to home. And ANIK D was a C-band satellite that made a lot more power. And the C-band is lower frequency. It has a broader beam and it's less atmospheric penetration. So it's better suited for the northern communities. Now, I'll just mention one thing, is that, if I can get these synchronized. Okay, before ANIK F2, we went to ANIK E, which was a 3-axis stabilized. The one you saw before was this canister here. This was a spinner. It was easy to keep attitude control. The satellite spun. The reflector didn't. It stayed pointed towards the Earth. It was mounted on a D-spun shelf, but it was an inefficient because only 1/3 of the solar arrays could be used. And then there was ANIK E, ANIK F1, ANIK F2. And I'm going to jump to ANIK F2. And it was, again, the most powerful satellite built to date. This is an early picture, an artist's conception. Those solar arrays weren't quite like that. They didn't have the concentrators, those flaps on the end. But what's notable is it introduced the first CAE band commercial service in the world. And CAE band's an even higher frequency. It's a 20-30, 20 transmit, a 30 receive. And CAE band, by being at a higher bandwidth, has by being at a higher band, frequency band, has much more bandwidth. It's much greater. You can carry way more information at those frequency. What's the disadvantage of CAE band? Well, the technology was more complicated, the receivers, the amplifiers, all that, but also it's at a higher frequency, so it produces narrower beams. So you have many spot beams that they try to arrange contiguously. And that's why you have those reflectors on the side, this assembly of 5 reflectors on each side. They were for the different beams that covered the North America. And also, it was the first instance in which there was onboard processing, because on a satellite, typically you send a signal from the Earth, and then the signal comes back to the Earth on an X-band downlink, where it's demodulated, it's gone to baseband. They decide where to send the channels and who should pay, and then they send back up. They remodulate it and send back up. So, so that makes for a double hop. And it's not practical if you're trying to do telephone or video conferencing by satellite, because you got about 0.15 second to go up, 0.5 second to go down, and the second up, 0.4. So you got 4 times 0.15 seconds. So you're over half a second. Any processing time is extra. And then the signal has to come back. So you're up to 1 second or more, which makes a phone conversation very difficult. So the SpaceMux was an onboard computer that could basically reduce it to baseband, decide everything, and then skip that second hop. And then let's not forget about the Canadarm. And the Canadarm is has been an achievement. The first Canadarm was fantastic. They built one. Canada paid for it, but when US paid us for all the other shuttle. The second Canadarm was mounted on the ISS and was the reason we built the ISS. Now, we only built one, but we got the Canadian astronaut programs and all the training in the US in return, and shuttle flights up to the space station. And it established Canada as a world leader in space robotics. There was MSAT 1 and 2, the first mobile communication by satellite. And it was mobile like in a truck where you had a receiver in a truck, but it established us as the pioneers in CAE band. And CAE band is, in L band. L band is a lower frequency, good penetration for telephones, but it is difficult because you have the problems of passive intermods. And passive intermods is when you send a signal, a powerful signal, it was about maybe a couple of 100 watts exiting to MSAT is the one on the right. It had two 6-meter reflectors, so one for transmit, one for receive. So if you're transmitting the signal, if there's any nonlinearity, like a metal to metal contact, a piece of dust or something like that, you produce these harmonics. And given that the received signal is 100 million times 100 million times weaker than the transmit signal, it takes only a very small harmonic to mask the incoming signal. And of course, the transmit and the receive signals are a different frequency, but if you have a harmonic that falls in this one, at the satellite, you might be creating a noise that's hiding the signal from the Earth. And we developed this technology in Canada, and with that, we did most of the L-band feeds around the world, and they got a lot more powerful. We got smarter. There's Inmarsat 5, Inmarsat XL, AlphaSat. This might be Inmarsat XL. It had a 20-meter reflector, and the feeds there were combined transmit and receive. The PIM performance, or the passive intermods, had to be down 150 dB. So it's we had to train everybody, including the janitors, including, it was in a special area, no dust, no nothing. It's fairly tricky to make these things without PIM. Also, we built radar satellites to observe our coasts. And I'm sorry, I'm turning at the screen, so I'm turning away from the video here. But the radar satellite, the first one we built, it was the most powerful synthetic aperture radar. It was a 15-meter deployable SAR, or synthetic aperture radar antenna. It wasn't quite an active antenna. It was a slotted waveguide. It had a few phase shifter. But then we continued on and we built RadarSat 2. And RadarSat 2 was a direct radiating array. It had some subarraying, but it was a direct radiating. It had a lot more modes it could do in the radar. And that one is still working as of today. And in 2019, we launched the next generation, which was RadarSat Constellation mission. It was launched on one of the very first SpaceX, 3 satellites at the same time. That was a bit of an ordeal. And the advantage, again, we used newer technologies for the direct radiating arrays these satellites could be flown in tandem, and there were many things you could do in tandem. But as one example, if you see a ship off the coastal water, a RadarSat, it's in a kind of polar orbit, and it processes around the Earth. So it might take 20 days before you get back there and the ship's not there. So you never know what happened to it. But if you have 3, you can trace it. Is it coming in? Is it going out? And which direction it's going, as one example. And here we are today in 2021. I didn't, oh, sorry. One more story. We built all the motorization and half of the control electronic for ExoMars rover. ExoMars is going to be the first European rover, and it's to be launched early next year. Its main objective is to search for signs of life on Mars, and it it has many experiments on board, but when it has, it's a drill that can drill down 2 meters, because they figured that at 2 meters, life wouldn't be killed by the ultraviolet radiation that is bombarding, because there's no atmosphere to absorb it on Mars. And this was the actual motorization carriage that was built. And here are the wheels. Those wheels have two sets of spring, one to flatten like a tractor and then one to act as a shock absorber. They were quite contrived to build. And now we are today. What's happening today? Well, today there's two really big projects going on. One is Telesat Lightspeed. Telesat Lightspeed, I explained the satellites in GEO, but if you want to have satellites closer to the Earth, to have the same ping time as fiber or something like that, you need many satellites to cover everybody on the Earth at the same time. So Telesat Lightspeed has almost 300 satellites. And these satellites are on a number of orbits. There's so many satellites per orbit. There's maybe, I think there's maybe 6 polar orbits, and there's 20 incline orbits, and the satellites are daisy chained, will be daisy chained around these orbits. And what's different from this constellation that other constellations don't have? Well, for one thing, it's a broadband CAE band. It's going to have as innovation a direct radiating array CAE band. So this is really going to be the first real commercial use of this. And like Iridium, which is a constellation just for phones at L-band, low bandwidth, the satellites talk to each other, meaning if you want to send a signal to, let's say, halfway around the Earth, sends a signal to this satellite, to this satellite, to this satellite, and goes down to the others. So in a similar way, this is going to have optical intersatellite links. So another innovation to be used commercially. So the optical intersatellite links, because in optical you have very high bandwidth, you can put a lot of data through it. So they will connect the different satellites like a network of connections, and then you can send a signal from satellite to satellite and put it down in the right place. There's a few CAE band constellation you hear about. SpaceX has one, and Worldview has another one. But those constellations, well, they're really at the infancy compared to this one. First of all, they can't talk between the satellites. So you have to be in view of a ground station. And some of these constellations, the ground segment or the ground station, you need so many of them, it costs more than the satellites, the whole satellite network you're putting up. Whereas this only needs a reasonable amount of ground station to operate the satellite. So this project is being built now. Canada has put in about $1.5 billion loan, and Quebec government has put in a $250 million for work that will be done here, and the Ontario government has put in about $100 million. These are all, of course, loans that depend on your performance. So if you succeed, you don't have to pay it back, kind of thing. And then the other important thing that's happening these days is that the US started the third space station, the Lunar Gateway, and they also started to work on the lunar base on the South Pole. So that's Project Artemis. So they're working on that, and the Gateway is going to be the next space station. It's going to have a Canadarm 3 that's going to be on it. And what's the innovation there? Is this arm is going to be controlled by AI, because we have Canadarm2 is operated by operators at Johnson or at the space agency here, and they look in the camera and they grapple the shuttle before, and now the different modules that go to the space station, and they plug it into the space station. It'd be kind of too dangerous to let them dock directly. So the Canadarm does this, and we control it, we see it, we aim the target, we grab it. Whereas this arm here, because of the communication delay, because it's in a halo orbit around the moon, this station. A halo orbit just means like the moon is here, and it just goes around, and it always faces the Earth. So you always see the space station, and it precesses with the moon around the Earth. So the lunar the moon precesses in 28 days around the Earth. So in 28 days, so the orbit rotates on itself in 28 days. So so the Canadarm 3 is going to be, I think, a large part of it is going to be the artificial intelligence. Now, so with the space station, one of the big things is going to be if we want to explore the solar system, explore the moon, is going to be, well, fuel is the biggest problem. It's this one single biggest problem. And to get fuel, it costs a tremendous amount to launch it from Earth. That's why the gateway is built around the moon, because there's a Lagrangian point around the moon. The Lagrangian point is where the gravity of the moon, the Earth, and the sun cancels out. So it's kind of in the vicinity. So it's a very small gravity well. So it doesn't take a lot of energy to leave. The Earth, it takes a lot of energy to leave the Earth and to go into orbit, but then it takes a lot of energy to leave orbit and to go towards Mars or towards the moon. And something leaving the lunar gateway will not have to use up all that fuel. So it'll have a lot more fuel to accelerate and get there faster and brake, etc. So it costs so much to get fuel from the Earth. Oxygen is the main thing, the oxidizer. It's the main weight, and you burn up about 80% of it on a rocket going up. The new Starship they want to build, SpaceX, when it gets to the lunar gateway, it would only have 1/9 of its fuel. And you need kind of like 8 other missions to fill it up of oxygen. So the cost, the time, the risk is incredible. If you could get oxygen, number one, and then maybe hydrogen and water out of the moon, which is right there, and a small, relatively small gravity well, it would be much, much cheaper, much handier, much faster. And it just so happened that the lunar regolith, what is lunar regolith? It's the lunar dust and unconsolidated rocks that is on the surface of the moon that you can scoop up. But the lunar regolith contains, in some places, about 40 to 45% water. Now, not water, sorry, oxygen. And how does it have this oxygen? It has it in iron oxide, in titanium oxide, in aluminum oxide. So with a process to take out the oxygen of these oxides, but you get the metals, the aluminum, the titanium, the iron, but you also get the oxygen. So there are a number of experiments that have been built, and there's one being built in a course here at McGill just this semester, well, this year, to basically extract the oxygen from lunar regolith. And so kind of new race has begun to create the infrastructure for space exploration. And the number one thing is fuel, and the number one thing in fuel is oxygen. And the Chinese and the Russians are working together towards that. Then iSpace in Japan has signed an agreement with Israel to work on that. So people are starting to realize that this is extremely important. And in Canada, Canadian Space Mining Corporation is leading this effort to create a Canadian kind of space mining, lunar oxygen extraction, fuel extraction, water extraction system. So this is my last slide, Richard, so you won't have to take your cane out. So uh, Canada has always been a leader in space. I think I tried to show you there's many, many, many more firsts and accomplishments that were done in Canada. But we, like Richard said, we're the only country that actually makes more money from space than is spent by the government. And many of the technologies that we develop are in fact standards and common use by all the companies in the world. So we were definitely a leader, still a leader. But space exploration is entering a new phase. And in situ resource utilization, that's ISRU, will be one of the major building block, an essential building block for great ease in exploration. And Canada has the world leadership on the utilization of space, but it also had leaderships on mines and its financing. So the intention and the hope is to be able to combine these two and again become the leader in this infrastructure that we need for space exploration. So so I finish on this thought that Canada is in the opportune position to further its global leadership as we enter this new phase of space exploration. So thank you.
So let me ask the first question. Isn't there water on the moon? I'm sorry? Yes, they should. Yep.
Okay, I'm gonna.
We're trying to make this happen in real time, so please.
Okay, can you repeat?
Isn't there water on the moon?
Well, there is certainly evidence of water on the South Pole, but it is at the bottom of craters, very deep craters, and it's not going to be so easy to get the water straight out of there. You're talking about going, you know, a mile deep in a crater, and you're talking about no heat. It's really the coldness of space. You're not looking at the sun. You're not looking at the earth. So it's extremely cold, and it can be extremely difficult to get water. But, you know, that's going to be part of Artemis's mission.
What is going to be Canada's contribution?
Well, Canada's contribution is on the Deep Space Gateway is Canadarm 3. Canada is looking to contribute a number of rovers. So that's being discussed yet. It's not yet funded except at the development stage. And of course, with the experiment, with this development of a process to extract oxygen from regolith, this could be another way, in perhaps a simpler way to get oxygen. And there's still going to be the problem of storing it and transferring it, but we can see how that can happen.
We have a few questions coming in. This one we're going to love. The oxygen extraction experiment at McGill, is it based on molten regolith electrolysis, carbon reduction, or hydrolysis?
Well, Richard, you're in charge of that experiment. So you.
I think the answer is going to be, last year we did the molten regolith electrolysis. We're planning to continue that aspect and deliver the better. There is a second question, and first outstanding mark is the question starts with. It starts well.
It starts well.
Okay. All right. Thank you very much for telling me. I have this problem of muting and unmuting. You know, it's something that will carry to my death, I'm for sure. What is the timeline for the construction of the first moon phase?
Well, the timeline was for this the Lunar Gateway and the moon base. Now they've just been decoupled by NASA, but it was around 2024, 2025. The latest news was that it might be delayed by a year because they're having trouble with the spacesuits. The spacesuits are quite complex, it's a dusty environment, and that's putting maybe a year's delay on the program.
All right, we have, can you elaborate on the use of AI in the space program?
Well, AI that Canada is involved with will be for the Canadarm. So it involves having the right type of cameras to get a stereoscopic vision of it, the right kind of targets, no doubt some other kind of sensors, force moment sensors on all the joints and mechanisms and the latching end effectors, and so that you can actually tell that it latched, and a number of sensors there. And all of this will be combined in AI to direct it, to dock it, and to know that it's properly docked. So there's, because it's a little bit different in AI on the Earth, because everything has to be fail-safe. You're talking about human lives, or you're talking about, you know, hundreds of billions of dollars of investment. Anything has to fail in a fail-safe position. So that is actually very complex to do, and AI adds another level of complexity to do this. So there's going to have to be a lot of work done on AI and fail-safe mechanism.
And so what Canada gets out of the deal?
Well, what Canada gets out of the deal is, well, we're going to further our premier position on space robotics to have this additional, I was going to say feature, but it's more than a feature. It's a great capability, okay, to have AI in the space robotics. So we're the world leaders, and we're taking it to the next step. So definitely, it's a huge advantage for Canada.
Another statement that says thank you, but and I'm gonna state it out loud because I think that was the very new and novel part of your presentation was the old RCA story, which I am very happy that you were able to express, and so of all the other development as well in early Canada. So what do you foresee is the next step for us?
Well, the RCA, I touched on it relatively briefly, but between RCA and Canadian CMC, we spurred a whole technological movements over here in Montreal, and the technology, communication technology, and the signal transmission capabilities were all started from Canada, from here in Montreal, and we're distributed. But this created a big economic system over here, and it spurred economic development in these areas in Canada and in Montreal.
Thank you very much. I would like to ask Yves Beauchamp to come and thank you in the best way possible. Hopefully not with a kiss.
Oh, j'ai été vacciné 2 fois.
J'ai été vacciné 2 fois. Alors, merci beaucoup. So I would like first to thank the Montreal chapter for organizing this event. Please thanks Ron for your leadership in the Montreal chapter. It's very important for the Academy. So on behalf of the Canadian Academy of Engineering, I would like to thank you, Mark, for this great presentation. It was fascinating to learn more about the space program development, especially the way you did, and some major Canadian innovation. To be honest, never again will I look at Gramophone the way I see. So it's really started all, so it's very amazing. So as fellow, we are all proud of being Canadian, and I'm sure that after your presentation, all of us will feel even prouder of being Canadians. So thank you so much, Mark, for this great presentation. Great. And I would like to mention that Mark has been nominated as fellow this year, for those who don't know. And I welcome also L'Entrecier, who is this year the honorary fellows, which is the highest nomination we can give to any of the members. So thank you, all of us, of being here. So great. That's it. Thank you. Bonne soirée.